glad you're here. I just last night. So for those who took it, how was it? Good. Not so good. Maybe a little. Lots of thumbs up. See you over there. Good stuff. Good stuff. Oh, lots of thumbs up. None of you guys took it. None of these guys took it. No, they're joking. They're actually down. But I'm glad to hear it went well. We're going to get started with some calc today. So let's remember at the very end of last week, we talked about the relationship between area under a function and anti-differentiation. I hope that's the conclusion that we were able to come to at the end of last lectures of last week. And now we're able to finally get to the fundamental theorem of calculus. So let's remind ourselves what these four parts say. The first part tells us that if you have an antiderivative, we can tell the entire area underneath the function just by the value of the antiderivative at the endpoint over an interval. Now the second part tells us that the integral and the derivative are inverse operations. We're going to try and use both of these parts of the fundamental theorem to help us solve some questions. Now the other thing we said last week is that this week is going to be full of a lot of evil questions. I just want to make sure you all know, before we get started, a lot of these questions will be way more difficult than the questions that you'll be seeing on any tests. I think it's just better to see these evil questions now instead of just so we are extra prepared for the test. I hope that's okay with everyone. So, without further ado, we're going to get started, okay? So this first question says, okay, if possible, let's calculate the area underneath the curve for the function f of t is equal to 3t squared on the interval 0 to x for any x bigger than 0. Now the reason we have to ask the if possible, let's go back to our first fundamental theorem of calculus part here. Remember that it says f has to be integrable. So what does it mean to be integrable? So a function is integrable either if it's continuous, or continuous, or if it has jump discontinuities only. I guess possibly holes. I'm not sure. We don't see holes very often. So continuous or jump discontinuities. The important thing is a function is not continuous if it has asymptotes. So let's try and use this here. So this example says we'll calculate the area underneath the curve for the function f of t is 3t squared. So our goal is to find the integral from 0 to x of f of t dt. That's going to be nothing but the integral from 0 to x of 3t squared dt. Now let's remember at the end of last class we did the same example but with a huge Riemann sum. We're not going to have to simplify that this week. All we're going to have to do is remember that our integration rules will have 3 times. We'll use our inverse power rule here. So we've got t squared. We'll add 1 to the power. So we'll get 3 cubed. We'll divide by the new power. So we'll do 1/3. And we'll integrate from 0 to x. So that'll be t cubed from 0 to x. So that'll give us x cubed minus 0, which is x cubed. Okay, perfect. That's not too hard, right? So I'm going to give you guys an example. If possible, I'd like you to calculate the area under the curve for the function f of x is equal to 2x to the power of -2 on the interval of -2 to 2. Okay, take 30 seconds, try it really quick. Feel free to talk with a neighbor if you like. All right, let's try it out here. Let's try it. So if our goal is to calculate the area under this curve, let's try, we'll take the integral. We want to go from -2 up to 2 of f of x dx. That's going to give us, we'll have the integral from -2 up to 2 of 2x to the -2 dx. Why don't we try our reverse power rule here? So we'll add 1 to the power.
So we'll get 2 times x to the negative 1, and we'll need to divide by the new power. So we'll divide by negative 1. And we'll evaluate that from negative 2 to 2. Maybe some people already see it. This is going to give us, we'll have 2, I'm going to turn this negative 2 times 1 over 2, subtract negative 2 times 1 over negative 2. So this will give us negative 1 minus 1 equals negative 2. Let's think about that for a second, okay? So the area under this function is negative 2. Does that make sense? We should always do a little sanity check after doing questions. I like sanity checks a lot because they help us see if our answer might be correct. So we'll take a look at the graph. Remember, the graph of 2x to the negative 2, that's going to look something like this. You'll notice the key thing about this graph, went to eraser mode. The key thing about this graph here is it is always positive. It's always above the x-axis. So does it make sense for us to get a negative area? How could this have happened? Anyone have any ideas? Yeah. Exactly. Our function was not integrable because we have an asymptote here at 0. So it's important to remember, okay, when are we able to use our fundamental theorem? When are we not able to use it? And although we might not be able to solve this type of integral in our calculus 1 course just yet, it's possible we might be able to develop some of those tools later on. Is everyone okay with that example? All right. So let's try out some other ones here. We're going to go over this example here. So this says we're going to let f of x be the function of the integral from 0 up to x of the square root of 1 plus t cubed dt. And it asks us to find f prime of 6. So here we're going to think back to the fundamental theorem part 2. So the fundamental theorem part 2, that tells us here, we're going to scroll all the way back up. If we take the derivative with respect to our function, where our upper bound is x of our function f of t dt, that's just going to give us nothing but f of x. So I'm going to scroll back down here. So by fundamental theorem 2, f prime of x should be equal to, let's just take our x here and we'll sub it in everywhere we see it a t. And we'll remove the integral sign. So that'll be the square root of 1 plus x cubed. So if it tells us to find f prime of 6, then we can say f prime of 6 is equal to, we'll sub in x everywhere we see it, and we'll get the square root of 217. So that example seems pretty easy, or not too bad. So let's see. By the way, I wrote that it's not testable. This is absolutely testable, so I'm just going to scroll this out. That was a mistake. But my question for you all is, let's try and compute this result here. So let's find the derivative of the integral 2x plus 1 up to x squared of e to the negative t squared over 2 dt. Okay, take another minute, discuss with a neighbor, and we'll convene. Just a sec. What does my teacher mean? People in the last section asked that as well. So if you have distance, right, a function of distance, the first derivative is the velocity, right? What's the second derivative? Just shout it out. Acceleration, right? So do you know what we call the third derivative? Jerk. We call the third derivative jerk. So this shirt says don't be a jerk. Yes. Little fun calculus joke there. Anyway. All right. So let's take a look at this problem here. Has anyone been able to get a solution for it? Let's try and, I don't remember how to solve it. I don't know what the solution is. So let's try and solve it together, okay? So our question says to compute the result, it's asking for the derivative of this integral. My first question for you is, are we able to apply the fundamental theorem part 2, like in our last question? Are we able to apply the fundamental theorem? What do we think? Let's get some maybe thumbs up, maybe thumbs down. Just see what we think. Or maybe we're not sure. Maybe we're not sure. Well, let's take a look back. We'll look up. So remember, our fundamental theorem part 2 tells us that the derivative of a function is we can only substitute this x in if we have an x in the numerator and a constant in the denominator. So the problem with this integral here is we have a 2x plus 1 and we have an x squared. These are both functions in x. So in order to integrate this, we're going to need to do a little bit more work. I know you guys have a child's math problem for this one as well, or a function that's very similar. I think it's a root of something else. So let's see if we can solve this kind of problem together, okay? So remember, let's try this. I'm going to generate a new function called f of t, and I'm going to make our new function just be the inside, e to the negative t squared over 2. Okay, cool. Now, so this derivative of the integral is going to turn into this, the integral of f of t dt. Okay, cool. Now, by our fundamental theorem part 1, by fundamental theorem of calculus part 1, this is going to be equal to f of x squared minus f of 2x plus 1 for some antiderivative f. Oh, sorry, just the integral part so far. The integral of that is equal to f of x squared minus f of 2x plus 1 for some antiderivative f. So far this is all good. We don't know what the antiderivative f is, but the key thing about this question is we don't actually have to. Let's see what we can do. Apologies for anyone writing on pencil and paper here. I'm not going to recopy that down, but we'll take the derivative of both sides. Now, the good thing is this is exactly what we want. Our left side is exactly what we wanted to solve for. So now let's just see if we can do manipulations on the right side to get our final answer here. So our derivative of this, we'll take the derivative term by term, and let's remember to some of our rules from a couple weeks ago. This is going to be f prime of x squared times, shout it out, 2x, minus, we'll have f prime of 2x plus 1 times 2. Cool. Now we know that since f is an antiderivative of f prime, by our fundamental theorem, we'll have f prime is equal to small f. So this is the same as small f of x squared times 2x minus small f of 2x plus 1 times 2. So all we're going to do here is we're going to sub in our values of small f right into this equation here, and we should get e to the negative x squared squared over 2 times 2x minus e to the negative 2x plus 1 squared over 2 times 2. All right. Is everyone happy with that one? Any questions about that one? So this should help out. Now we have a value for that derivative there. If you need to calculate something else, say for your child's math assignment, you might have to plug in a number into your x. But this is the general picture of the way you could solve that kind of question. All right. Any more questions about that one, or we'll move on to some of the tricky parts? I see some people still look like they're looking really intently. Oh, yeah, question?
How did you do that?
Okay. How do we do which part? Which line is the confusing part?
All of it.
All of it. Who feels the same way? Do we want to walk through that one more time? All right, let's walk through that one more time. So Thank you for letting me know, by the way. If you're ever confused about something and want me to go over something again, please just shout it out. Like, that's what I'm here for. So basically, the key thing that we realized here, if we look only at this integral, oh, no questions.
Why does this have x and t?
Why does this have x and t? Good question. So we'll start peeling back the layers here. We're gonna be we'll be like an onion today. We'll peel back all the layers. So we learned last class that we could define a function in terms of an integral. So for example, do you remember last class when we looked at the area of x from 0 to x of t squared dt? Do you remember that? No? That's okay if not. So I'm actually going to switch to our last week's tutorial notes really, really quickly. So does this look familiar to everyone when we calculated the area underneath this curve of 3x squared? Or sorry, the integral under this curve right here. We have the function f of x is equal to 2x. We calculated the area under this 2x here, right? What we were looking for was really, what is the area of some arbitrary function t when we integrated some arbitrary function f of t? So the thing is, when we actually have a variable in an integral, so for example, f of t dt, that t is just a dummy variable. You could call it whatever you wanted. So the reason why we have an x and a t there is so that we don't confuse what's in the upper bound and what's in our function. So I'm going to switch back to our current notes really, really quick. So the reason why we have the x here, the x's in the bounds, and we have the t not in the bounds, is so that we don't confuse what's a variable that's being integrated and what variable is being used to evaluate the bounds. Does that make sense? We don't want to integrate a function of x. We want to integrate a function of t and then evaluate it at some arbitrary points. Right? Do we have any more questions about that part? Okay. So now let's talk about the part of, okay, why are we doing all of this stuff? Because it looks like we're just pulling stuff out of nowhere, right? Where did we pull out that capital X? Where did everything happen like that? So let's suppose we didn't want to do that. Let's suppose we wanted to evaluate the integral first and then evaluate the derivative, right? That's probably what you thought to do at the very beginning of the question, right? So is it possible to evaluate everything that's highlighted there? Is it possible to take that integral? You might be unsure. The answer to this is actually no. Integrals that are of this shape or of this flavor are actually pretty infamous. We cannot take the integral of e to the something squared, at least not with our tools and single variable calculus. So we need to develop some other techniques to be able to solve this integral. So what we did was, we know the function is continuous, so some integral exists. We just can't write it in math terms. The same way, remember back in the first couple weeks when it was like, find the inverse of this function, and it was like, sine something, and we couldn't actually find an inverse using that. But we could find an inverse using specific points, specific numbers, right? This integral does exist, but it cannot be written in math. So we're just gonna call it big F. We'll just call it big F, and then what ends up happening is when we take the derivative, it ends up simplifying out. So we called our integral big F. We used the fundamental theorem. So this is by fundamental theorem 1. Fundamental theorem part 1, which gave us this. Then we took the derivative of both sides. So we took the derivative of both sides by x. And then we lucked out. We got only f primes. And f prime is what we actually know. F prime is the original function. Big F prime is our little f that we find to be the integrand. So our little f prime, or sorry, our big F prime is just our little f. So we substituted that back in right here. And then we just plugged in our function here. Does that make sense? Yeah, question right there.
So if we don't get all of that prime, we did not continue.
If you don't get, sorry?
If they're not all that prime, like capital F prime, we just not continue.
We might not be able to. The thing is, with questions that are of this shape, of this flavor, because we have our fundamental theorem part 2, we should be able to find a solution. We've got a definite integral with bounds in only x. We're taking the derivative with respect to x. There will be a way that it should all cancel out nicely. Yeah. So just assume that if you're not able to perform the integral itself, you will be able to solve the question, given a question like this, just using this method. Any other questions? I know I mentioned this last week, but I really, really like this tutorial section because you guys asked a lot more questions than the previous section beforehand, and we're able to have lots of great discourse. So with that out of the way, I told you we're going to do some evil questions. We're going to do some evil questions. We're going to do a little back and forth. I'm going to show you a tool that we can use, and then I'm going to give you a little bit more of an evil one. So we're going to quickly remind ourselves of what a u sub is. So I'm going to rewrite this integral as e to the negative x dx. This is a little bit easier to take a look at. Now, we don't know what this integral is yet. But we know what the integral of e to the something is, like e to the u, for example. So let's try and make a clever substitution here. If we say that u is equal to negative x, which is this thing in the exponent here, then du will equal negative dx, and then positive dx will equal negative du. So we're just isolating, moving around the dx to the du's. I'm going to plug in du, negative du, everywhere I see the dx here. So that's going to turn into the integral of, we'll have negative du, and we'll have e to the power of u. So everything we did in blue, that was our substitutions there. So now we can integrate this. We know the integral of e to the u du. That's going to give us e to the u again. That's really friendly. We'll have a plus c. And then all we have to do is sub back our original equation to get it in terms of x. So we'll be left with e to the negative x, negative e to the negative x plus c. Is everyone happy with that example? So now we did a somewhat easy u sub. We're going to try a little bit of an evil question. So let's try and find this integral. We've got the integral of 1 over 1 plus e to the x dx. That 1 is looking rather inconspicuous, but we'll see it kind of ends up messing with everything. So let's say 45 seconds, try it out for yourself, and we'll reconvene. You'll probably want to do this one with a neighbor as well. Let's suppose we just tried to use a regular u sub. Let's suppose we tried to use u is equal to, 1 plus e to the x. Du is equal to e to the x dx. We're met with a problem here. Because if we try and substitute like this in, we don't see anywhere where there's an e to the x dx. We can't find a way to do our u sub. It just won't fit. This square block won't fit into our circular hole. So let's see. Let's try something else here. This is perhaps the easiest way to solve this. We have to recognize that 1 in the numerator is the same as 1 plus e to the x minus e to the x. Divided by 1 plus e to the x dx. This thing right here, if we just simplify out the fractions, that's the same thing as 1, bless you, 1 minus e to the x over 1 plus e to the x dx. Remember, we can separate our integrals out by sums, so this will give us the integral of 1 dx minus the integral of e to the x over 1 plus e to the x dx. Oh my gosh. Now we can use our u sub. Because we've got a 1 plus e to the x. The derivative of 1 plus e to the x is e to the x dx. That's right there. So we found a way to do our u sub here. So we'll use this same u sub down here. So also, let's just evaluate this first integral. That'll just be x. We'll subtract the integral of, we see our e to the x dx here. That's going to turn into du. And our 1 plus e to the x, we'll sub in a u down here. Now we've got only u's in our second integral, so we can integrate that. We'll be left with e to the negative ln of the absolute value of u. That's just from our table of integrals, plus c. And then we can substitute in for u. We'll substitute our x values back in, plus c. So now you see what I meant by evil, right? Is everyone okay with that example though? After we found that little adding zero there, we're able to find our final answer using a u sub. Let's try another example. We'll try another example here. So, example, let's try and find this integral here. So we're integrating the function 1 over x squared plus 2x plus 1. This doesn't look too bad. Let's remember our denominator is in the shape of a square. So that's going to be the same thing as 1 over x plus 1 squared. Integral of that dx. So we can evaluate, we'll perform a u sub here, because we see an x plus 1 in the denominator, and we also see that the derivative of x plus 1, which is dx, is in our equation. So we can say u is equal to x plus 1, then du is equal to dx. That's really handy. It's right there. So we can perform this substitution. We'll get 1 over u squared, and then this is a du. That's going to be the same thing as the integral of u to the negative 2 du. We'll use our inverse power rule here, so we'll add 1 to the power. We'll divide by negative 1. We'll add c, and then we'll substitute back. So we'll get negative x plus 1 to the negative 1 plus c. Okay, awesome. So that was relatively painless. Now we're going to try a little bit more difficult of the example. I'm going to add 1 in the denominator again. So we've got the integral of 1 plus, integral of 1 divided by x squared plus 2x plus 2. So I'll give you another 45 seconds to try this example, okay? Give it a try. You might need to talk with a neighbor. Let's take a look. So, we did something similar in the last question with our square. So we'll notice it looks like it looks like we can do something similar here. Let's put it in the shape of that square here. So we can express this as x squared plus 2x plus this 2. I'm going to write that as 1 plus 1. I'll write that as 1 plus 1 here. Oh my gosh. This is just our square from our last question. So this is going to be the integral of 1 over x plus 1 squared plus 1 dx. And now it looks like we can make a clever use of again. So I'm going to let u equal to x plus 1. Then du is going to be equal to dx. So we'll substitute that in here. We'll get the integral of 1 over, we'll get u squared plus 1, and our 1 dx, that'll just turn into du.
We've seen this integral before, haven't we?
What's this? This is the integral of what? Just shout it out. Arctan. This is the arctangent of u plus c. So we can substitute our value for u back in to get it in terms of x. And this integral will be given by arctan of x plus 1 plus c.
All right, is everyone happy with that? Maybe not happy with it, but
It's a little bit fun. All right, so let's try this one. Now we know this from our table of integrals as well, but let's just remind ourselves that's equal to negative cosine of x plus c. So let's see if we can use that. We've got the integral of sine x dx. Do we have the integral of sine squared x dx?
take another 45 seconds and we'll read the action. Now, what's super important about this one is, although you might not be tested on it in this course, you will probably see it again in future courses. So actually, some of my friends over there had a contest a couple weeks ago that actually appeared on it, and almost none of us could do it. So I'm just showing this so this will hopefully prepare you for your future course.
All right, let's give it a try. Let's give it a try, shall we? So we're gonna think back. We're gonna think back to sorry? Never mind. We're gonna think back to some of the trig identities we know about. So this one's really handy. I'm sure we've all seen it. Sine squared x is equal to, I'm gonna just write it like this. Sine squared x plus cos squared x is equal to 1. We'll just rearrange that one a little bit. We also know, this one might be a little bit more tricky to remember, but it's the double angle identity. So cos of 2x is equal to cos squared of x minus sine squared of x. If we substitute that here, we'll get cos squared of x minus 1, minus 1 plus cos squared of x. So that'll give us 2 cos squared of x minus 1. So if we solve for cos x, that'll be cos of 2x plus 1 divided by 2. I just moved it around to the other side. Aha, okay. So this integral of sine squared x, that's going to be 1 minus cos squared of x dx. Oh, sorry, this should be cos squared of x, shouldn't it be? Yeah, that should be cos squared of x down there. So now that we've got this value of cos squared of x, let's sub that in all the way over here. We'll get the integral of 1 minus cos of 2x plus 1 over 2 dx. We'll take a pause really quick. Is everyone okay with all the J subs being made? I thought I heard the word no. That's okay. A lot of hand waving. That's okay. Are there any steps that you'd like me to quickly take a look over again before we keep going? Let's press on. We'll press on. So, oh, yes. Step 1 and 2 again. Which two? This one and this one? So we know sine squared of x. So here, we know sine squared of x plus cosine squared of x is equal to 1. So all we did was we rearranged that. This is a separate identity that we knew from the beginning. And all we're doing is we're going to sub that in. We'll sub the two equations together to get this. Is that okay? Awesome, thanks. So from here, we'll break up this integral into two integrals. We'll get the integral of 1 dx minus the integral. Oh, actually, you know what? Sorry, I'm going to do one more thing. This 1 and this negative 1/2, I'm going to cancel those. So we'll get 1/2 minus 1/2 cos of 2x dx. Now we'll try splitting up those integrals. So we'll get the integral of 1/2 dx minus the integral of 1/2 cosine of 2x dx. We'll move that over here. We'll try a u sub as well. So we have this 2x inside of the cos here. Let's try u subbing in u for that. So we'll get u is equal to 2x. Then du will be equal to 2 dx. Oh, that's handy. We've got a dx right here. So we'll substitute that in. The integral of our 1/2, here I'll do this one a different color. That'll just give us 1/2 x. We'll subtract, this will be the integral of 1/2 times. From this, we'll get that dx is equal to 1/2 du. So we'll substitute that 1/2 du in here for our dx. And then our cos of 2x will turn into cos of u. We'll take another quick pause here. Wait, this is a 1/2. Another quick pause here. Is everyone okay with that u sub we just made? Yeah, question? So this, if we expanded the fraction, we'd have cos of 2x over 2. The distribute the minus in, we'll have minus 1/2. So 1 minus 1/2 is 1/2. Is that okay with everyone? Good question. All right, so after performing that u sub, we'll evaluate here. This will give us 1/2 x minus the integral of, we'll collect our fractions. So 1/2 times 1/2 is 1/4. And the integral of cosine of something, that's the sine of u. There are no more integral signs, so here we'll add our plus c. And then we'll substitute our value for x back in. So we'll have 1/2 x minus 1/4 sine of 2x plus c. Okay, is everyone all right with that one? Yeah? This one is probably tougher than what you might expect on tests, but I don't write the test, so don't quote me on it. Okay. We're gonna move on. We're actually moving pretty fast paced for what we've got. I'm gonna quickly skip over this question. I think this one is actually way more difficult than the kind of integral you'll get, at least at this stage, but if we have time for the end, we'll come back to it. We're gonna quickly look at a question about curves, integrals between curves. Is Tristan here, by the way? Oh, you're Tristan. Oh my God, that's awesome. So let's talk about Tristan, guys. Tristan loves riding his bike, and he also loves going for walks. He's choosing between walking and cycling today. He bikes at a velocity of u of t is equal to 1/2 t squared, and walks at a velocity of v of t is equal to t. So the question is, how much more distance can you travel by bike in 10 minutes? So let's take a look at what this graph is going to look like. So I'm going to draw it out here. We've got this graph. this is going to be his walking speed. His walking speed is going to be like this. And his biking speed, as you know, you guys ever start off in a bike and it's a little bit hard to get going, but then once you're going, you're way faster than everyone walking. So it's going to be like this. And we want to find the time, the area between 0 and 10. So remember, since we have velocities here, our area underneath the curves is going to represent the distance. But we don't only want the distance. We want the distance more that is traveled by the bike. So what we're going to do is we're going to need to try and be able to integrate between these two curves. Now the other thing we're going to have to do here is find the intersection points here, because we're going to have to perform two integrals. So let's find the intersection point first. So remember, the way we find our intersection points, we'll set these curves to be equal. So t is equal to 1/2 t squared. 2t is equal to t squared. So 0 is equal to t squared minus 2t. Then we can see our answers are t is 0 and t is 2. Awesome. So they intersect right here at the very beginning, and they intersect at t is equal to 2. My scale looks really messed up, by the way. That's fine. So we're going to have two integrals here. We want to find the distance more that the bike will be traveling in 10 minutes. So let's see. We're going to have the integral from 0 to 2 of, we'll have t minus 1/2 t squared, because our blue curve is higher than our red one here, dt. And we'll add the integral from 2 to 10. This one should be a negative curve, by the way, because we want the more distance from the bike. We'll add the integral from 0 to 10 here of 1/2 t squared minus t dt. And we'll evaluate these integrals here. So the integral on the left, actually we can just distribute, you know what? I thought I had made a mistake in the previous tutorial with this question, but I think it's actually fine. This is a little bit silly. I think we can just integrate this here. We'll distribute that. And then we have the same integral, don't we? 0 to 2, and then 0 to 2 of 1/2 t squared minus t. I'm going to have to take a look at this afterwards, but I think this should just be the same integral. So we'll be integrating from 0 to 10 of 1/2 t squared minus t. Aren't they? They're the same integral, right? We have these two things on the inside are the same. We're joining them from 0 to 2 and from 2 to 10. We'll just combine them into a single integral here. When we integrate, this will give us 1/6 t cubed. We just use our inverse power rule. Minus 1/2 t squared, evaluated from 0 to 10. Remember, the fundamental theorem tells us that this is okay because our function is always continuous, both of them. When we evaluate, we'll get 10 cubed over 6 minus 10 squared over 2. We'll subtract 0, subtract 0. That's 0. That's just from this 0 component here. So that should represent the extra distance we got from Michael. Don't know what exactly that is. I think if you do that in your head, it should be approximately 117, but I'm not sure. So check that on your own. Question, yes?
If you can't visualize the graph, how do we know if it's precise?
Good question. If you can't visualize the graph, how will we know if it intersects? We just got to get some practice on finding intersections, either visually or you can set them equal to each other and try and see if the equation has a solution. Question? Oh, scroll up. Yeah, of course. Okay, now I want to take a little bit of a segue away from the problems here. We do have one more integral that we could solve together. We got a question back there, yeah? So we have made this integral negative because we want how much more distance was traveled by the bike. But in this region here, the bike is actually slower than the bike is slower than walking. So we took since the walking is above, we wanted to negate that basically it doesn't matter. You could have jumped straight away to this integral and it would have been fine by subtracting it. Is that okay? Awesome. Good question. Yeah, I actually messed up this question in the tutorial before this. It was a little bit silly, but it's all good. I've got a question for Tristan. What do you prefer? Walking or biking? Biking. All right, good stuff. I know you had only mentioned biking, but we needed an area between curves question, so I hope this is okay. So, I want to sidestep away. Do you guys have any questions you want to see from child's math? Any that you can think of right away? If not, I also want to show something else. Does anyone happen to have an imaginary calculator on hand? Can I borrow yours really, really quick? Thank you. Okay. Because I don't have one, on me at least. I'm going to switch over to the doc cam. This is really important. So, is it working? I guess it's not working now. So, okay, perfect. Okay, this is really awesome. So everyone's seen your calculator before. I forgot to show this to the last tutorial, but this is really, really important. If you ever have a question on a test where it asks you for the derivative at a point, or if it asks you for a definite integral, did you know your calculator can actually solve that? So let's take a look here. So in the top left here, you see how there's a button that says ddx? So if you want a derivative at a point, let's say we want the derivative of 2x, or sorry, derivative of x squared at x is equal to 1, we know that should be 2, right? So we're going to take the ddx, shift ddx, oh, might be in a different mode. Do you mind if I change the mode really quick? We'll take the ddx of, we're going to have to type in down here, we'll go alpha x squared. Does everyone see that? We'll go comma at the point 1, and when we evaluate this, that gives us 2. Okay, so let's say we were going to do the opposite. So let's say we wanted to integrate the function. We want to integrate the function 2x, and let's say we want to integrate it from I don't know, from 0 to 3. So the integral from 0 to 3 that should be 9, right? 3 squared. So let's integrate 2x on the interval 0 to 3, and that gives us 9. So it only works at a point, unfortunately. But if you have derivative at a point, or the integral, that's definite integral, you can solve it with your calculator. So make sure to make use of this. Thank you very much for letting me borrow my calculator. All right, so